So in this section I'm going to talk about Lagrangian mechanics, right? It's section 3. And when I prepare the course, maybe I've been a little bit overambitious. So a lot of the theory I will skip. I will focus on the main theoretical results. I will present them and apply them on practical examples. Okay, so we've talked about constraints before. But suppose that we have n particles, right? And that we write the second law of Newton for each of these particles. You know that this is a vector equation, so you have to write it for each of the 3 Cartesian coordinates, right? So you would end up with 3n differential equations. But that's of course an oversimplification, because you have to take into account the constraints that limit the motion of the system, right? And for instance, a very straightforward constraint is in rigid bodies, right? Because the distances between the particles are fixed. Well, you have linking forces, and you remember that these internal linking forces, they cancel out. So you end up with far less than 3n equations. Okay, the constraints that we'll consider in this course are called holonomic constraints, right? This means that they can be written in this form. This is not very important because in reality it goes far beyond the scope of this course. This is why I've mentioned it as for your information. But in practice, what does that mean? Well, it means that a particle is, for instance, constrained to move on a curve or on a surface, and the equation of that curve or surface is acting as an equation of constraint. We have already seen something similar, for instance, with the mass on wedge example, right? Well, the wedge was acting as a constraint. Okay, so these constraints introduce 2 types of difficulties. Well, the first difficulty is that the coordinates are no longer independent, and you end up with equations of motion that are not all independent. Right? So remember, in the case of the mass with a pendulum, you ended up with 2 differential equations, but they are coupled, right? Another difficulty is with the linking forces. Yeah, the linking forces are not given a priori, so they are among the unknowns of the problem, and they must be eliminated. For instance, in the case of the mass and pendulum, you had these 2 linking forces, F12x and F12y. You didn't know these up front, so they had to be determined and eliminated from the problem. And you had something similar with the wedge and mass problem, where you had a linking force R that had to be determined and eliminated, right? Well, the idea with the Lagrangian mechanics is that you don't care about the linking forces, or they are not part of the problem, so you don't have to eliminate them. This is what we'll see later on in the course. Okay, so far we have been using this Newtonian approach, and we have, well, often used Cartesian coordinates, right? And for a system of n particles with no constraints, well, we've seen just before that we have 3n degrees of freedom. Of course, if you start to introduce constraints, right, and suppose we have k constraints of this holonomic type that are link the variables, then instead of having 3n independent degrees of freedom, well, you have 3n minus k degrees of freedom, right? And for some systems, well, the degree of freedom that are left are not so easy to determine. So this is what we'll see in the next slide. So in general, the degrees of freedom, the number of degrees of freedom is n minus k. In the previous example, we were working with a system of n particles, okay, and each particle has 3 coordinates, right? So this is why n in this example is n equals 3n. But of course, in general, you could have particles and you could have rigid bodies, and you know that a rigid body needs a description with 6 variables, 3 in translation and 3 in rotation. So this gives a slightly more general definition, and remember that k here is the number of holonomic constraints. Well, a formula that might come in handy to compute the number of degrees of freedom is the following one, and it will be explained next. What do you see here in this formula? Well, A is the number of degrees of freedom in the given space. For instance, if you work in a plane, well, A will be equal to 3. NP is the number of parts of the mechanism, and PM here is the number of links with degree of freedom, with m degrees of freedom. So for instance, if you work in a plane, right, and you have something like that, you have a link like this, well, this will allow only movement like this, so this is 1 degree of freedom. If you work in space, right, not in a plane, and you have a ball joint link, right, well, you have a movement like this, okay, you have one like this, and you have one, well, like this, that you can turn around, right? So you have 3 degrees of freedom. So this is a 3 degree of freedom link in space, and here you have a 1 degree of freedom link in a plane. What we can say is that the number of degrees of freedom is a characteristic of the system. It does not depend on a particular choice of set of coordinates that you have made. So here's the formula to determine the number of degrees of freedom, and remember that A is the number of degrees of freedom in the given space, NP is the number of parts in the mechanism, and PM is the number of links with degree of freedom m. And so these are my 2 examples. I have here a closed chain, and I'm working in a planar example here, so I'm working in a plane, and here I have an open chain that can be seen as a kind of a model of a crane, right? So in this example we have A equals 3, and what is in common also is NP is the number of parts in the mechanism, and in both cases it's 4. So let's see what this formula gives us with this A equals 3. So it will be 3 times NP minus 1, okay, just to give you an interpretation of the formula. So A equals 3, so you have a sum from m to 1 to 2, so we'll first write it down for P1 times A, that's 3, minus 1, minus P2, 3 minus 2, right? So if we look here, the number P2 well, we see that it's equal to 0. There are no links with 2 degrees of freedom. So this means that this formula here, well, we can cross out the last term, and it's just a matter of seeing how many links we have with degree of freedom 1. And here, if we look at P1, we see that we have 4, and in this case we have P1 equals to 3. There are 3 links with 1 degree of freedom. So we have our formula. Yeah. In this example here, we know that MP is equal to 4, so I can replace NP by 4. So we'll have 3 times 4 minus 1 minus 4 times 3 minus 1 over here. And if we do the calculation, we have here 3, 9. Okay, here we have 2, so it's 9 minus 8. So this gives us 1 degree of freedom, and indeed I think this is also what you would have expected. So let's write down the formula for the open chain. The beginning is exactly the same. Okay, since the number of parts in the mechanism is the same, and we're working also in the same planar space, and A is equal to 3, and the difference of course will be over here. So now we only have 3 for P1 times 3 minus 1. So here we have 9 minus 6, so this produces 3 degrees of freedom. So this one has 3 degrees of freedom, and this one has 1 degrees of freedom. So this is an illustration of this formula. So remember that in the beginning you have 3n equations, right? Since you have k constraints, right, you do eliminations until you have 3n minus k equations that are left, right? Well, instead of using 3n Cartesian variables, the idea is to use what is called generalized coordinates. These are variables that are links to the degrees of freedom. Yeah, you know, here in this case we have a system with n particles, k constraints. Well, there are 3n minus k degrees of freedom, so you can find 3n minus k generalized coordinates that are linked to the degrees of freedom. Okay, the Cartesian coordinates, they come neatly in groups of 3, right, per particle, but of course for the generalized coordinates they will not divide in convenient groups. Yeah? What you can say is that of course you can link these types of position vectors, let us say in the Cartesian coordinates, to the generalized coordinates q1 to q3n minus k. Yeah, and this gives you transformation equations to go from one set of coordinates to the other one. Okay, we'll now review the concepts of degree of freedom, constraint, and generalized coordinates that we've just introduced on a very simple example, which is the mass on an inclined plane, and then we'll review it also in an example that we already know, which is the pendulum on mass. Here the mass is constrained to move in a planar movement, right, and it's forced to move on this inclined plane, and you have its equation over here. So it's very obvious that you have only 1 degree of freedom. Yeah. The constraint is obvious also, and the movement of the mass, it's planar, that's one constraint, and then it has to move on the inclined plane, and the equation of the inclined plane is over here. Yeah, so here we have an example of a holonomic constraint. And then, well, of course, since you have 1 degree of freedom, you're looking for a coordinate that is associated to this degree of freedom, and of course it's kind of obvious, right? So you choose Q because it's associated to the degree of freedom. And if you would use the standard Cartesian reference frame XY, well, you can look for a link between XY and Q. And in this case, it's kind of obvious that it's given by these equations. So these are transformation equations that allow you to go from the generalized coordinate to the Cartesian coordinate. But of course, what is important to see is that the general motion can be completely described by the coordinate Q. So we can forget about this Cartesian coordinate frame XY. Okay, this is our pendulum on card system that we already introduced before, so I won't go in the details of that again. And we can have a look how we can find out about the degrees of freedom. Well, we know from our exercise with Newtonian dynamics that we had 2 differential equations, so we know that the degree of freedom is 2, right? But this is a good exercise to apply the formula that you have here. Okay, so we can ask ourselves in what space we're going to work, and in my example I've chosen to work in space. The number of parts in the mechanism, yeah, so you have the pendulum, the cart, and the rail. So NP equals 3. And then you have links. You have a link, it's a pivot over here. It has 1 degree of freedom, and then you have a slider here. So it has also 1 degree of freedom. So here we have P1 equals 2, and P2 equals P3 equals P5 equals to 0, right? So now we can write the formula. There is only 1 term that will give you a contribution over here. It's m equals to 1. So 6, that's A, that's NP, that's my P1, the only one that's giving a contribution. That's my A again, okay, and the one that's giving a contribution is m equals 1, so we have 1 again over here. So we obtain 2. You could do the same exercise again with A equals 3, it would work also. Okay, we would have 3 times 3 minus 1 minus 2 times 3 minus 1. Okay, so that's 6 minus 4, and that's 2 also. Okay, remember that we had constraints in the system, and they are the following one. x2 is equal to x1 plus L sine phi, and we had y2 is equal to L cosine phi, right? These are the 2 constraints. Well, this one here can be written differently. And so if you write the first equation as x2 minus x1, you have L sine phi. Okay, so now you can see that if you square this one and you add the square of this one, you'll have L square, and this is a form of a holonomic constraint, right? We have again this equation as a function of the variables, the coordinates, which is equal to 0. Okay, so we've seen that the linking equations can be like that, and the linking equations, well, this is actually giving you the movement of the rod, right, of the pendulum, and you see that it's, well, parameterized by the variable x1, which we have called x, and the variable phi. So we see that the complete motion can be described by the variable x, which is the degree of freedom of the cart, and phi, which is the degree of freedom of the pendulum. So we'll use x and phi as generalized coordinates, right? And this is something that I've written or drawn for the Newtonian approach. And in this Newtonian approach, well, you see these linking forces appearing, right? And it was kind of annoying and tedious. We had to eliminate them. You will see that in this new approach that we will be seeing in the Lagrangian approach, these linking forces will never appear. Okay, we will ignore them in the problem, and this will make things easier, maybe not for this rather simple pendulum on cart system, but if you have more complicated systems, you will have more linking equation, and this will make the Newtonian approach more complicated. And this is why often, well, for more complicated examples, we go to the Lagrangian approach.